April 1912. The Titanic was the largest passenger ship in the world, carrying more than 2,000 people across the North Atlantic. It had watertight compartments, electric warning systems, experienced officers, and a reputation for engineering confidence. None of those things could compensate for one decision made on the night of April 14th. The ship kept its speed. Throughout the day, Titanic received multiple reports of ice in the region ahead. Captain Edward Smith knew that ice had been sighted near the route. Darkness was approaching, the sea was unusually calm, and without waves breaking against an iceberg, floating ice would be harder to see. There were two obvious options: turn farther south or slow down. Titanic did neither in any meaningful way. Shortly before the collision, the ship was traveling at roughly 22 knots. The British inquiry later concluded that this speed was excessive under the circumstances, and that the collision was brought about by the speed at which Titanic was being navigated. At 11:40 p.m., Lookout spotted an iceberg directly ahead. The bridge reacted immediately. The helm was turned, the engines were ordered astern, but a ship more than 269 meters long could not erase its momentum. The iceberg scraped along Titanic's starboard side, opening the hull across several compartments. The ship sank less than 3 hours later. More than 1,500 people were lost. The iceberg was natural. 22 knots was a choice. Northern Italy, 1963. The Vajont Dam was an engineering monument. Rising more than 260 meters above the valley floor, it was one of the tallest dams ever constructed. The concrete wall itself would survive the disaster almost perfectly. The people below it would not. The danger was not inside the dam. It was beside the reservoir. Monte Toc, the mountain overlooking the artificial lake, had shown signs of instability for years. Cracks appeared. Sections of earth moved. In November 1960, hundreds of thousands of cubic meters of rock slid into the reservoir, generating a wave that should have ended the experiment. Instead, operators continued filling and lowering the reservoir while studying how the mountain reacted. The assumption was that the landslide could be controlled. By October 1963, the slope was moving dramatically faster. Engineers knew a major collapse was increasingly likely, yet the reservoir remained high enough for a gigantic displacement wave to become possible, and communities downstream were not evacuated in time. At 10:39 p.m. on October 9th, roughly 260 million cubic meters of rock and earth broke loose from Monte Toc. The mountain entered the reservoir at enormous speed. Water had nowhere to go. A wave surged up the surrounding slopes and over the dam, then crashed into the valley below. Longarone was virtually erased. Nearly 2,000 people died. The dam remained standing. Technically, the concrete worked. Everything around it did not. Tenerife, March 1977. Two Boeing 747s were on the same runway at Los Rodeos Airport in the Canary Islands. One belonged to KLM, the other belonged to Pan American. Neither aircraft was supposed to be there under normal circumstances. A bombing at Gran Canaria Airport had diverted traffic to Tenerife, crowding a smaller airport with aircraft it was not designed to handle. Then fog arrived. Visvisas collapsed. The Pan American 747 was instructed to taxi down the runway and leave through an exit. The KLM aircraft was positioned at the opposite end. Radio communications became confusing. Different crews used phrases that sounded similar to formal air traffic control language. Transmissions overlapped, and then one decision converted confusion into the deadliest accident in aviation history. The KLM captain began takeoff. He did not have final takeoff clearance. The Pan American aircraft was still on the runway, hidden by fog. Its crew saw the KLM jet emerging from the mist and tried to escape by turning left and applying full power. The KLM pilot saw the obstacle and tried to rotate early. For a moment, the aircraft became airborne. It was not enough. The KLM 747 struck the Pan American aircraft and crashed farther down the runway. 583 people died. The investigation identified several contributing factors, including fog, radio terminology, airport congestion, and communication failures. But one fact remained central: the runway was occupied. The aircraft took off anyway. Cape Canaveral, January 1986. Space Shuttle Challenger stood on the launch pad after one of the coldest nights ever experienced before a shuttle launch. Engineers from Morton Thiokol were worried about small rubber seals called O-rings inside the solid rocket boosters. The seals had shown erosion on previous flights. Temperature made the problem worse. Cold rubber becomes harder and responds more slowly. On the evening before launch, engineers reviewed the data and recommended that Challenger should not launch below 53 degrees Fahrenheit. Forecast temperatures were far lower. The initial recommendation was simple: do not launch. Then came discussions between managers and engineers. Takeoff management reconsidered. The recommendation was reversed. NASA received approval to proceed. The next morning, ice covered parts of the launch structure. Temperatures had dropped into the teens overnight. At 11:38 a.m., Challenger lifted off. A seal in the right solid rocket booster failed to function properly in the cold conditions. Hot gases escaped through the joint. 73 seconds after launch, the vehicle broke apart. All 7 crew members were killed. The Rogers Commission later described the launch decision as flawed. Decision makers had not been given the full history of the O-ring problems, nor the strength of the engineers' objections. The shuttle had engines, computers, redundant systems, and thousands of carefully inspected components. A rubber ring helped destroy it. Mamajnachin had already been warned about the rubber ring. Chernobyl, April 1986. Reactor number 4 was preparing for a safety test. The purpose sounded reasonable. Engineers wanted to know whether the turbine's remaining momentum after shutdown could temporarily provide electricity to emergency equipment before backup generators reached full power. The test had been attempted before. This time, delays pushed the procedure late into the night. The reactor's power dropped far below the intended level. Instead of stopping the experiment and allowing the reactor to recover safely, operators continued. Control rods were withdrawn to raise power again. The reactor entered an unstable condition. Several automatic protections were bypassed or prevented from interrupting the test. At 1:23 a.m. on April 26th, the experiment began. Seconds later, conditions inside the reactor changed rapidly. Operators pressed the emergency shutdown button, but the RBMK reactor contained a lethal design flaw. Under those specific conditions, the initial movement of the control rods could briefly increase reactivity instead of immediately reducing it. Power surged, fuel channels ruptured, explosions tore open the reactor building, the graphite moderator caught fire, carrying radioactive material high into the atmosphere. 2 workers died immediately or within hours. 28 emergency personnel died from acute radiation syndrome in the following weeks, and the long-term health consequences extended far beyond the plant. Later investigations emphasized that Chernobyl was not merely the result of operator mistakes. Reactor design defects, poor safety culture, secrecy, inadequate procedures, and institutional failures all mattered. But there was still a moment when the test could have ended harmlessly. The reactor had fallen into an abnormal condition. The decision was made to continue. The safety test destroyed the machine it was supposed to protect. North Sea, July 1988. Piper Alpha was one of Britain's most productive offshore oil platforms. On the morning of July 6th, maintenance workers removed a pressure safety valve from a condensate pump. Because the work was unfinished, the open pipe was temporarily sealed with a blind flange. The pump was not supposed to operate. That evening, another condensate pump stopped unexpectedly. Without it, production would soon have to shut down. The night crew needed a replacement. They chose the pump that had been under maintenance. The problem was information. The permit showing that the safety valve had been removed was not effectively connected to the decision being made in the control room. The operators believed the pump could be restarted. It could not. When the pump was activated, pressurized condensate escaped through the temporary flange. A gas cloud formed. Then it ignited. The first explosion damaged other equipment and started fires across the platform. Oil and gas continued feeding the flames through connected pipelines from neighboring platforms. The fire intensified until sections of Piper Alpha collapsed into the North Sea. 167 people died. Later investigations exposed failures in permit-to-work systems, emergency preparation, fire protection, communication, and management. The disaster was larger than one pump, but the sequence began with a simple assumption. Someone believed a machine was ready. No one had made sure. Gulf of Mexico, April 2010. The Deepwater Horizon drilling rig was completing work on the Macondo well, nearly 5,000 feet below the surface of the Gulf of Mexico. The well had been difficult. Cement had been pumped around the production casing to isolate oil and gas deep underground. Before temporarily abandoning the well, the crew performed a negative pressure test. The test was supposed to answer one critical question: was the well sealed? The readings did not make sense. Pressure appeared where it should not have been. At one point, Approximately 1,400 pounds per square inch remained on the drill pipe, while another line showed 0. That discrepancy was a warning. The test should have demonstrated that the barriers were holding. Instead, personnel interpreted the results as acceptable and continued operations. Heavy drilling mud was then displaced from the riser with lighter seawater. The mud had been helping suppress pressure from the reservoir. With that protection reduced, hydrocarbons began entering the well. There were more warning signs. They were recognized too late. Gauze raced upward through the riser and reached the drilling rig at approximately 9:49 p.m. on April 20th. Explosions tore through Deepwater horizon. 11 workers were killed. The rig burned for roughly 36 hours before sinking. Oil then flowed from the damaged well into the Gulf for almost 3 months, producing one of the largest marine oil spills in history. The official investigation did not blame one person or one isolated mistake. It identified failures involving BP, Transocean, Halliburton, engineering decisions, cement design, procedures, training, regulation, communication, and risk management. But the negative pressure test was designed to reveal whether the well was unsafe. It did exactly that. The result was accepted anyway. 7 disasters, 7 different industries. Ships, dams, aircraft, spacecraft, nuclear reactors, oil platforms, and deep water wells. None failed because humans lacked information completely. Titanic knew ice was ahead. Vajont engineers knew the mountain was moving. The KLM crew knew clearance mattered. Challenger engineers warned about temperature. Chernobyl operators knew the reactor was outside the planned test conditions. Piper Alpha had maintenance documentation. Deepwater Horizon produced pressure readings that contradicted a safe well. In each case, the final catastrophe required more than one failure. Technology failed, procedures failed, communication failed, organizations failed. But somewhere inside each chain was a decision that removed one more layer of protection: continue at speed. Keep operating, begin the takeoff, approve the launch, continue the test, retard the pump, accept the pressure reading. Disasters rarely announce themselves with a single dramatic moment. Usually, the warning arrives first. The terrible decision is what happens next.